All right, welcome to another week of the 1212 lab here at North Georgia. So what we're going to be taking a look at this week is the determination of KSP for potassium hydrogen tartrate, which is just an ionic compound. And for this particular experiment, a lot of these ideas of like talking about KSP or just the idea of titrations are not things we've done a whole lot of yet in the lecture, probably things we're going to be getting to in the next week or so. But KSP is still just an equilibrium constant, and a lot of the titration stuff is really just some more solution stoichiometry. So none of these things should really be too bad to kind of adapt to upon seeing some of them maybe for the first time. So as a starting point, we're going to talk a little bit about KSP in terms of what it is. You'll sometimes hear it called the solubility product constant, but since it is a capital K, it is just another equilibrium constant. And what it pertains to is when you take an ionic solid and you put it in water to break it apart to its ions. That's the type of reaction that KSP corresponds to. And so as kind of a quick example, let's say we have the reaction of iron 3 hydroxide. We take that solid, we put it in water. It's going to break up some into iron 3 plus and 3 hydroxide ions. And if we wanted to write a KSP equation here, we can calculate KSP by doing products over reactants like a normal equilibrium reaction. But notice, and this will always be the case for all of these, our initial reactant's always a solid. We're only going to have the products that typically show up here. And that's why we call this the solubility product constant, because it's only the products that we're really looking at here because there are no reactants that we're going to see show up, because the reactants are always just going to be an ionic solid every time. Now, one thing we will have to be careful about for KSP in particular, we get spoiled a little bit in the acid-base chapter with all our stoichiometry kind of always being 1. Notice here the stoichiometry is not 1 for everything, and so if we have that coefficient of a 3 on hydroxide, that means we are cubing its concentration in the equilibrium constant calculation. Now, the other kind of term that we'll often hear with KSP is something called molar solubility. So to go over kind of what that is, it's typically the solubility of an ionic salt measured in just units of moles per liter. So it's kind of how many moles of that ionic compound will dissolve in 1 liter of water. And we can actually calculate this using KSP. Typically you're given one or the other, but they are not the same thing. And do pay attention to this, particularly in your lab. When you get towards the very end of the lab, some of the post-lab calculations have you using your solubility to find some information and kind of converting your solubility to other units. Make sure you are actually using the molar solubility for those, not the KSP. It's a pretty common mistake, I think, calculation-wise in this lab. Now, to show how these two are related, let's say we want to find the molar solubility of magnesium fluoride, given its KSP is 5.16 to the minus 11. So to show how this is going to work, what we're going to do is we can set up our equation for KSP. And for magnesium fluoride, this equation that I'm getting here is because if we take this solid and break it apart, we're going to get 1 magnesium ion and 2 fluoride ions. And so it's going to be magnesium 2 plus times the concentration of the fluoride ion squared. Now, notation-wise, typically we'll use either X or sometimes maybe an S for the molar solubility itself. And what's going to happen is that molar solubility is the moles of the ionic compound that dissociate. Well, for every 1 magnesium fluoride that breaks apart, we're going to get 1 magnesium ion. So really the concentration of magnesium 2 plus is the molar solubility in this case. But for the fluoride, for every 1 magnesium fluoride that breaks apart, we're actually going to get 2 fluorides. So the concentration of fluoride itself is actually 2 times the concentration of our molar solubility. Because basically for every one, because again, molar solubility is the moles of the ionic solid that are dissociating. But for every ionic solid here that dissociates, we're getting 2 fluorides. So the fluoride concentration is 2 times that molar solubility. And then notice for KSP, like if there's that 2 there, we are still squaring it also. So it is going to be X times the quantity 2X all squared. And then if we want to solve for our X, we can actually go ahead and do that. Right? So in this case, 5.16 to the minus 11 should be equal to, really if we expand all of this, 4X cubed. And now we can solve for our X value and find an actual molar solubility. And again, units here are going to be in molarity when we go through and solve it this way. And so these two things, like I said, molar solubility, KSP, they are related. Really, anytime we know one, we can always find the other. And typically just general setup-wise for molar solubility, when you're finding the molar solubility, the number of X you actually have here is going to match whatever the power you're raising that thing's concentration to. It's kind of a nice, easy way, I think, to remember this. So the reason there's a 2X here is because we're squaring it for the molar solubility, because there's 2 fluoride ions that we're getting for every one of our compound that dissolved. So the fluoride concentration is 2 times that molar solubility. And so I just want to, like I said, I'm kind of re-emphasizing that a bunch of times, because I think that's a common kind of confusion point for when we're going over this kind of material. Now, in terms of the reaction we're going to be doing in the lab, what we're going to be taking a look at, we're going to be looking at the dissociation of potassium hydrogen tartrate. And so that's this compound right here. This is the potassium hydrogen tartrate. It's going to break apart into potassium and a polyatomic ion that we can just call hydrogen tartrate. And you'll sometimes see this abbreviated as KHT for the potassium salt and maybe HT for the hydrogen tartrate itself. And what we're going to do in order to find our KSP, we need to know the concentrations of these two ions. But those aren't things that are really just easy to look at a solution and just immediately find or know. And so what we're going to do to try and find these concentrations is really going to try to find the concentration of this ion right here. Right? So that hydrogen tartrate ion itself is a weak acid. Right? That's why we see the one hydrogen written out in front while kind of the rest are kind of embedded into the formula. And so what we're able to do is an acid-base titration is what we call this. And what that's going to involve is reacting hydrogen tartrate with sodium hydroxide. And for every hydroxide that reacts with the hydrogen tartrate, we're going to get just a tartrate ion, and then we're making water. So it's kind of a basic neutralization reaction, or kind of the fundamental neutralization reaction that's happening. We have some sort of weak acid as a proton, we have our hydroxide making water. It's kind of the general reaction that's going to be taking place there. Now, the term titration, in terms of kind of what is the goal of a titration? Well, if I back up for 1 second, we said our goal is really to find this thing's concentration, because if we know the concentration of these ions, that's what we need for KSP. So our goal is really to find the concentration of that ion. So the purpose of the titration is then to find that concentration of that hydrogen tartrate. So the way that's going to work is if we have a strong base, in this case the hydroxide that we're going to add to our weak acid, if we know the concentration of our base, and we can measure how much of it we need to add to get to what we call an equivalence point, or really just to neutralize all the acid that is there, then we should be able to figure out that unknown acid concentration. That's kind of the general purpose or goal for most titrations that you'll see. And so now in terms of how do we know when we've reached this point where all of our acid is neutralized, or we've reached what's called this equivalence point, there's two ways this can be done. We'll see one in lecture, and that's going to be the pH curve. Probably won't really be doing that much here for the lecture, but we could plot pH versus how much of our base, that's the titrant in this case. The titrant's what you're adding that you know the concentration of. And so we could make this plot pH versus the volume of the titrant that we're adding, and we can find our equivalence point and how much of basically how many moles of our acid should be in our solution by doing that. We can also do one other way, and this is visually, and this is what we're going to be doing in our lab, is that we're going to be taking our acid solution and we're going to add something called an indicator to it. In particular, we're going to use phenolphthalein, which turns pink when our solution gets a little bit basic. And so we're going to have actually a visual color change for our titration that will happen when we're right around our equivalence point. That'll tell us kind of when that titration should be done. And again, if we measure how much base we added to get to that point where our reaction is done, now we can do our calculations to figure out how many moles of acid should have been there. We can find the concentration and eventually work our way to KSP. Now, a couple quick notes. To do our titration, most titrations are going to use something called the burette. This is kind of a slightly zoomed out version of what a burette looks like. It's a pretty long kind of glass tube, so you are going to have to be careful not to like drop or break these things. They can break fairly easily, and they are probably one of the more expensive pieces of glassware we use during the semester, so do take caution using them. This is kind of hooked up. There's a burette stand in here. Basically, it's a ring stand. We have a burette clamp that can hold the burette. And what you're going to do is you're going to fill this burette with your solution that you know the concentration of. And what this thing looks like, you can see tick marks a little bit from here. I'm going to have some other views of it here in just a second. These little tick marks, they're kind of like almost an upside down graduated cylinder, reverse graduated cylinder, because the larger numbers are on the bottom, and then like the zero is actually way up towards the top. But as you first start to fill these things, just kind of some quick things as far as like the bottom part of the burette, there's this little stopcock that has a knob that can turn. If you see the knob in this position where it's perpendicular to the actual burette itself, the rest of the glass tube, that's the closed position. That basically means all of your liquid that's in this glass tube is not going to go through and pour out the bottom. If it's open, that's when it's going to be parallel with that tube. That's when you're going to see the liquid actually drain out the bottom. So that's just kind of real quick, kind of closed, open, and that's how you're going to be adding solutions. How we can kind of control how much we add is that what we're going to do is we're going to look at our burette, and we don't always have to fill it exactly to the zero mark at the very top. Usually what we want is something a little bit below the zero, where all we want to do is measure what is the current volume before we start adding anything to our reaction. And that's really the purpose of the burette. We're measuring what is our volume of our solution that the burette is reading before we add anything, and then just what is our volume that the burette's reading after we've hit that equivalence point or see that color change, in our case, for our reaction. And so remember when you do read your burets, so for instance, if you're reading the buret that's here in this image on the right, you do want to give it, since all these tick marks are basically 1/10 of a milliliter, you do want to give a second decimal place. Right? So for this one, if we're looking at it, it looks like 1, 2, 3, it's maybe just past the 4th tick mark, so maybe like 0.42 milliliters or something in that range. If you think it's exactly on that line, say 0.40 milliliters is your initial buret volume. And then what you're going to do is add base to your reaction, do your titration, wait for the color to actually change, and I'll show some images of the color change we expect here in just a second. But then you can take the volume difference and figure out how much volume of our sodium hydroxide in this case was added, and that's what we can then use to start doing kind of our stoichiometry calculations to figure out how much acid we must have had in our unknown solution. All right, now the visual part of this, like I said, kind of how we know our reaction's done. We are going to use phenolphthalein as an indicator. It's going to change kind of to a pinkish color as we get to a more basic pH, and the more basic the pH gets, the darker that pink becomes to the point where it's almost a purple color. And so when you're doing this titration, your goal should really be to get a really faint, very, very faint pink color and not get all the way to kind of like a deep purple or a dark pink. And so here's kind of a couple examples as far as kind of what we're looking for. We want to see kind of that really pale pink color that just persists all throughout the solution. And even this, if you were in an analytic lab, is almost kind of on the verge of being too dark of a color. I mean, because it basically means we've gone farther past our equivalence point and just our measurement's not as accurate as it could be. If our solution's this color, we've gone way past our equivalence point. We now have a very basic solution, and that means that we can't really accurately determine how much acid was there. We're kind of overestimating it based on how much base we've added to get to something like this. So as you're doing the experiment, you are going to be doing 3 trials of this titration. I would at least aim to have one of your trials hopefully look like this towards the end. And to get something that looks like this, you are going to have to be kind of careful as you do the titration, particularly as you get around to where you know that equivalence point is. You're going to have to be very slowly adding, because it might only be 2 drops to go from this to this color-wise, which is not a lot, and so you have to be very careful and kind of cautious if you want to get kind of the most accurate results that you can out of this lab. And kind of on that note too, as you're kind of doing your titrations, I would say the very first trial, you don't have to add things super slowly, drop-wise. You can add most of your base relatively quickly in the first trial, just to kind of see when are we going to get this color change, so you have a rough idea of how much you need to add. And then what that lets you do on your second and third trial, so that those 2 trials hopefully in particular can be really accurate, is that let's say it took 25 milliliters of the sodium hydroxide to make it change color the first time. Well, for the second trial, you can add the base really fast up to say maybe 21, maybe even 22 milliliters, but then you're going to start adding the base really slowly, like drops at a time. And that way, when you're going really slow, it's much easier to kind of control things to hopefully where we get a nice, just very pale pink color and get a lot more accurate measurement as far as how much base was added and how much acid must have been in our solution originally. All right, now, at the end of all of this, calculation-wise, once we've kind of done our titration, just kind of real quick, kind of go through what are we doing with that information. We should have a volume of our sodium hydroxide solution that we use to reach our equivalence point. We should also have a concentration for that sodium hydroxide. It should be written on the bottles in the hood that have the solutions. And so if we have a concentration and a volume, we should be able to find the moles of our sodium hydroxide. And if we know the moles of sodium hydroxide, if we're at this what we call equivalence point, that's kind of what we're looking for, that really pale pink color should be right about the equivalence point, then we also know how many moles of our acid, the hydrogen tartrate, must have been in our original solution. And once we know that piece, now remember one of the things you'll be doing kind of at the start, the acid solution that you start with is going to be 25 milliliters for its starting volume. And so if you know the moles of the acid that must have been in that original 25 milliliters, now we have moles, we have the volume, we can find the concentration. And if we know the concentration of our hydrogen tartrate, now we can find KSP. Right? KSP for the potassium hydrogen tartrate, our initial kind of starting compound, it should be equal to the potassium concentration times the hydrogen tartrate concentration. But what's going to happen here, if we know the hydrogen tartrate concentration, since this is a 1-to-1 stoichiometry for that ionic compound, whatever our concentration is for the hydrogen tartrate, it's the same concentration for potassium. And so basically knowing this, we're going to know both of these concentrations, and we can find the KSP for our hydrogen tartrate. And so those are going to be kind of the calculation steps that we actually get to at the end this week. And so the experiment for this week, you'll get a little bit, it's kind of some new experience getting to use a burette. You'll also have something, we'll have a graduated pipette that you'll be measuring out some acid solutions with at the start too. That might be a little new, but that's not too bad to go through and actually kind of see the first time. And so a couple new things, but the actual lab itself is relatively short. And even if you end up doing more than 3 titration trials, like if you want to do 4 or 5, just to try to get all of them really accurate, you can still do all of those in a pretty reasonable amount of time. And then the calculations afterwards. I think hopefully this gives a nice outline for kind of what to expect. These calculations should be a little bit shorter than some of the KA lab calculations from this previous week. So hopefully shouldn't be too bad to kind of go through and find our KSP values. Probably the harder part won't be the calculations from the experiment itself. Probably the post-lab questions tend to have a few more calculations involved for this lab than some of the others. But hopefully that gives everyone kind of a good intro to what we're going to be doing this week and kind of a good idea of what to expect. And we'll see you all next time.